So what are we going to cover in this session? I hope this will be more in this particular session. We'll try to cover more practical case studies. I'll try to take at least one case study, which I'll run through, and the motivation will be what are the different challenges that we faced in production when we were working on this particular solution, right? What were the challenges which were thrown at us by the system, by the data, by user behaviors, and even when we were learning, what were the few things that we had to be aware of, right? So a running example would be that, and at the end, I will also have a couple of other examples, just to give you flavor of other things. Good. This is something that we have talked, but let me reiterate. So when you are developing your models, right, your solutions, what are the factors that will influence, your choice of models? Okay? And some of them is the scale of the data, right? I told you that when we are working with the instances, the impressions, when we show the search results against a given query by a user, we would have received multiple responses back from the system, and we show to the user. User will give us feedback by clicking or not clicking on those records, right? So these are the feedback, and these are the records that we showed. Now, when we gather it over a period of time, it runs into billions or hundreds of millions of records. So my choice of solution will be influenced by that. And then how do I model? How do I use my features? One question back to you. When you guys were doing logistic regression, Bayesian logistic regression, or recommender systems, what kind of features were you using? Let's say if there was, for recommendation systems, you had a user, you had an item. What kind of features were you using? Was it the meta features about the user or the item, or it was the user ID itself and item ID? Meta features. Okay. Right. So the good thing about meta features is that it is generalizable, right? But then there are certain things which, if in certain cases, when you have enough history about the IDs, about the users of the items, right? If you could memorize through your model, and this is what one of some of these big learning, pre-trained models, BERT and everything, they also have a bit of memorization embedded into them. Right? So if you could learn them, that will also be great. Now, why I'm telling you that is the features that you're using here, and some of the models could be the ID-based features. When I say ID-based features, what do I mean? I could use user ID as a feature. Okay. Now I have Flipkart has roughly around 300 to 400 million users, right? Such as the. So will you have so many parameters in your model? The answer is yes. Okay. How do you deal with it at prediction time? When you're learning, is one thing that you will have so many product IDs or user IDs, right? So product IDs will also run into millions. Queries will also run into millions, right? Now, when you combine them, the feature vector becomes very huge. If you are simply using one hot encoded features. Do you understand one hot encoded features? You do? How many of you can you raise your hands? Okay. One hot encoded is, let's say you have 10 users and you want to use them as features. So you create a feature vector of, I'm not going into collinearity, but you create a feature vector of size 10. Okay. Each index of that feature vector corresponding to a user ID. Okay. So it's a very sparse vector, right? For each user, only one of the index will be lit up and rest of them will be 0. Now, when you get a request, so you will learn the weight for that. During your model training, you will learn the weights for all of the indices. At prediction time, only one of them will be available, and which is fine. Okay. So that is one hot encoding. Now, if I do one hot encoding of the user IDs, product IDs, query IDs, and so on and so forth, not query IDs, but if the term IDs, the terms which appear in the query, search query, text query, right? The cardinality of your feature vector, it increases many folds. And then it becomes challenging for you. How do you learn in such a setup? Otherwise, you could do meta features, and we'll talk about that also. The other things, these things we have discussed, latency, what will be the impact on the latency because of the choice of model? How scalable will your solution would be? If you have such huge features and even you're working neural networks, beware that there could be challenges with neural networks also. Not always, but sometimes. The other thing is when you, okay, I remember that you guys have also gone through Bayesian logistic regression, right? So if I ask you to develop a model, and you will give me, let's say, a probability, it's a classification task. You will give me a probability of class being 1 or 0, let's say binary classification. But I also want your confidence in that estimate, the probability that you gave. You gave me a probability of 0.9, you gave me a probability of 0.1, but how confident is your model in that? How many of you can generate that probability, that confidence? Any idea how would you do that? There are two ways, I mean, at least 2 ways. So forget about this model, right? Remember, we were talking about the average age of a group, or if I have to ask you, right, average age of the group here, of the people here, or average age of students in IIT here, or average height of the students in IIT, how would you go about it? Will you go and measure everyone's? Maybe not. You will take a sample, right, and you will get your estimates from there. Now, when you get your estimate, there will be some variance, because if you had taken another sample, there will be the estimate would have differed. Right? So from one sample of the entire population, can you generate the variance and or the confidence? The answer is yes. Confidence intervals is that. So someone on the chat mentioned that we could use bootstrap sampling. So we could do bootstrapping when you are generating confidence estimates. And how do you do that? You train multiple models and you do that, right? You get your confidence, you get your parameter estimates, and then you take an average, you can take the standard deviation. That's one way. The other is, I know that you guys have also gone through Bayesian logistic regression. Okay. Bayesian logistic regression, instead of giving you one value of the parameter, it gives you a distribution of the parameter. Just like in this average height case that, or average age case that we talked about, there's a distribution. Let's assume, and you go through the law of large numbers or central limit theorem. More often than not, you will find that there is a Gaussian distribution or a normal distribution around your parameter estimates. If you have that, if you have such a distribution, and not restricted to Gaussian, but any distribution, then you can compute mean and you can compute the variance. And hence you can get your uncertainty in your estimates. And when people, when you guys have gone through Bayesian logistic regression, so even before I go into that, the classical logistic regression that you guys do, right? There is a regularization component also over there, so that you don't overfit your model. That regularizer, more often than not, will either be L1 norm or L2 norm, right? So L2 or L1. These regularizers in Bayesian world, they actually translate into, if you know the Bayes rule, if I want to predict my probability or my estimates of my parameters, right? These regularization components, they actually emanate from something called priors. I can have a prior knowledge about my, this is knowledge, this is belief, prior belief, that my parameters are normally distributed. The variance that I talked about, the uncertainty, that distribution will be normally distributed. Okay. There is another, so Gaussian is one, that translates into L2 regularizer. There is another regularizer which is L1 regularizer, and the corresponding distribution for that is Laplace. Okay. So it translates into having a Laplace prior on your parameters, and it translates into L1 regularization. So the whole point is that you're given a prior from Bayes rule. The likelihood is what you have learned about MLE, I think. How many of you understand MLE, maximum likelihood estimate? Okay. So maximum likelihood estimate is that you've been given a data and you assume a parameter, you try to fit that parameter to that data. Let's say you make an assumption this is Gaussian distribution or something of that sort. You maximize it, and argmax theta is the maximum likelihood of that. Right? In Bayes rule, if you have to estimate your parameters theta or W, which is a vector, right? It will be probability of W given data, which will be probability of data given W, Data given W is the likelihood. But how likely are you going to see the data if this was the parameter W, right? This is so far, probability of data given W or theta was your likelihood estimate, and this is what you have been dealing with so far. Now you multiply it by the base rule by PW, and under it will be P data. P data is probability of data which is going to be constant for all the parameters W. So you ignore it. It's called normalization constant. So PW. PW is the prior. So you would have, I'm just connecting the dots to regularization to Bayesian models, okay, through these priors. So PW is your prior. Now, if you look at the left-hand side of the equation, that is probability of your weights, theta or W given data, that is called posterior. If that also has a distribution, then you will have the confidence estimates, and you can also have your mean values from there. That's how you get your confidence estimates. Now, these are important because if the requirement for the model is to get the uncertainty estimates, the confidence estimates, then that is how you will develop your solution, right? Either you will have to resort to bootstrapping, or you will have to resort to a Bayesian model so that you can generate uncertainty estimates. Once you have uncertainty estimates, then you can do a lot of things from them. Okay? And we'll talk what you can do. The other factors that develop basically influence your models is the explainability. Explainability helps you with debuggability as well as other things. Typically, today a lot of focus is primarily on predictive modeling. So people focus a lot on the predictive power. Are you able to predict the right target variable or not, right value of the target or not? People focus a lot on that. Explainability has been an afterthought, but a lot of research has started happening in this field also. So toolkits like Lime or Maple, these are some of the tools that help you generate some explainability or interpretability of the models. Now, when you're developing your models, the other thing is that how is it going to be used? For example, if you're doing forecasting problem or regression, linear regression, then maybe the output can be used as it is. Unless you have transformed a variable, sometimes you transform the target variable also, okay, when you're doing the modeling. So instead of doing y equal to W transpose X, sometimes you need, in some cases, you transpose even your y's. So you learn a relationship log of y equal to W transpose X. And same thing could be applied also on the left hand, on the right hand side. You could also learn log of y equal to W transpose of log of X. But point is the target variable. If you are transforming it, then you need to, when you're predicting at that point in time, you have to transform it back to the real value, because the relationship that you learned was in a different space, was in a log space. Now there is classification, how your model is going to be used, right? If we generate probabilities from our models, but eventually you have to take a decision using those. Which class does that, the output, which class is my output suggesting, right? My input is belonging to. So fraud detection is such that you are, if someone on Flipkart is committing a transaction, right? Can I figure out if that user is committing a fraud transaction or not? We have seen such cases happening over there. Now I'll learn a model which is a classification model offline. It will give me a probability score. But at runtime, when I have to apply and figure out if the user is going to commit fraud or not, then I have to use the threshold. So you have to play around and tune the thresholds in your offline data to figure out what will be the right thresholds. So that's another use case. The third is ranking. If your entire purpose was to just rank the content, when a query is fired to get you the results. Now the query could be in the form of search query. So I will show you search results. For recommendation systems, user comes on a page and you will show recommendations. So the query there is user and his or her prior history, right? So I have to show the list of results to the user. Okay? In the same way in ads, we show ads, a bunch of ads. If the objective is just to show a ranked order, then I have multiple ways of basically using that model. Maybe I can use probability, maybe I don't need to. Like I said, if you are using logistic regression, then the logit function, the sigmoid function on W transpose X is a monotonic function, right? So I don't need to transform, I don't need to compute the probability there. because the rank order is not going to change. So I can simply use W transpose X and it saves me a computation. I don't need to do an exponential. I don't need to take an inverse of that and so on and so forth. Now this thing is applicable even in not only when you're predicting the probability in a point-wise learning, but it is also applicable to pairwise learning. Before that, I go into this. How many of you are aware of learning to rank field? Okay. Learning to rank is simply given a list. Okay. How do you generate the optimally ranked list? So a ground truth has an order has been given to you that this is the right list. This is the right ordering of the items in that. Right? If you look at it, it's n factorial. Actually, when you look at the potential number of lists that you will have will be n factorial. So learning is cumbersome. I mean, of course, you can't, for a given list, you can't compute n factorial possibilities, potential candidates, and then learn on top of it. But it's a problem, all right, that you have to address and solve, right? And then when you are doing learning to rank, then there will be corresponding metrics also, which say that this rank list is a better list than the other one. I described the INDCG metric in the beginning, or mean average precision one. So you can measure those metrics also. Now, if you have to do learning to rank, so learning to rank can be done in multiple ways. I can't do n factorial computations when I'm learning. So I resort to some assumptions offline in my model. Those assumptions are, now you see that the points are independent of each other, even though they are part of the list. I'm saying that they are independent of each other, which does not make sense, because if the query was Nike shoe and I'm showing first result also as a Nike shoe and second result also as a Nike shoe, the relevance of the second item now, or the clickability, goes down in the presence of the first one. There is an impact. There is a second order impact here, or an effect. But I'm making an assumption, and modeling is all about assumptions. You would have heard of that proverb that all models are wrong, some are more useful. Okay, so we make that assumption, and we say that these are independent, and then it boils down to simple point-wise logistic regression kind of models, point-wise classification problems. That what is the probability of an item being relevant, right? But if you truly go into these ranking models, there is another flavor. What you could do is, let's say there are n points, you can form NC2 pairs, okay, potentially. And in those pairs, you will have a relationship if first item, one of the item is better than the other item or not. So now you can compare one item against all of them. Okay? So this is called pairwise learning. So you can do pairwise learning also. So this is an example. The second bullet point here is pairwise learning to rank with logistic regression. What you do here is that if I know x1 is better than x2, right? I'll translate my problem into this. My label now has changed. My label space is now x1 is better than x2 is positive label, class 1. And it's a symmetric relationship. You can flip it around. X2 is poorer than x1, so it will be 0 or -1, whatever be the class representation that you have chosen. But if you look at this one, this does pairwise learning. At the same time, when you are predicting, you simply have to predict, because feature vector x is given to you, and you are learning w is shared here. Okay, even in the pairwise learning, you will be learning on w transpose. You will be simply learning w transpose, and at the time of prediction, it is as good as doing point-wise prediction. So you can do learning in a pairwise fashion, but a prediction in a point-wise fashion. Okay, and the point here is that the sigmoid, the monotonic nature would still be applicable. And Bayesian personalized ranking for recommendations is such an example. So I've just put a reference here. It postulates a recommendation. So, you know, in recommendation, when you are doing recommendations, I can also formulate that problem as a matrix completion problem, right? There is a matrix of user and items. On the rows will be user and the columns will be items, right? So when I do that, you will realize that the cell that I have in my training data, which is populated, it is based on the interaction. Had the user interacted with that item in the past or not? And then I will do matrix factorization and other things, right? Now what is happening over there the cells which are empty in recommendation world, you typically don't know the label of them. You assume them to be negative, but they may not be negative. Correct? So they're not zero. So this paper actually, what it does, it postulates the problem in a different way. It says that I don't know negative, but what I know is that user has interacted with this item, and I'll assume interaction as a preference. But user prefer this item over the other ones which I haven't shown to the user. So they flipped it around. So it made the label slightly softer. They're not hard negatives anymore. And you get a lot more labels, yes. Right? And then the formulation is this only. So it's a logistic log loss only. The formulation is this only. I mean, sigmoid of W1 transpose X minus this one. In matrix factorization world, the W transpose X is basically, you don't worry about that, but it's the embeddings of the user and the embeddings of the product multiplied together. So this is a case study. Remember we talked, I talked a lot about the CTR or click-through rates or conversion models. This field on its own is called response modeling. I mean, how is user responding to the data or the content that you've shown? Okay. So the response could be in the form of a click, or the response could be also in the form of a conversion or a purchase on e-commerce platform. So you can postulate it as a probability of click once you show the result, or probability of buying it. But both of them are, as of now, you can treat them as binary classification problem. But if you look at it, I can also formulate it as a learning to rank problem. I'm showing a list in the presence of the other, how would user actually react or respond to one. But as of now, let's focus on this one. This is a problem that we have to solve in Flipkart, and we have been solving it actually. There are multiple ways of solving it. Some of the challenges of the problem is that of this particular problem is in real world is of imbalance. The data is imbalanced. Then you would yourself see the number of products that are shown to you. How many of the products will you click on? You will only click on one, right, against the search result. And this is a phenomenon which is present, right? So your click-through rates, the number of times you showed the result and the number of times you got a response back from the user, it will be very sparse. So the order of 1 by 100, 2 by 100, 3 by 100, that's the order. Conversions are further sparser, okay? They will, given a click, how many times will you convert? That is also the same order, and hence, when you showed the result, which is called an impression, when you impressed an item, how many times will the user click? This is the level of imbalance that you will see. X into 10 raised to the power minus 4, right? X could be 1, 2, 3. It's a single digit. X is single digit. Okay. Now it has an implication. How do you train your model? We talked about dealing with imbalance is tough. When you train your model, there is a possibility that your model could be biased because of the majority data, and hence you will start predicting negatives a lot. So you could deal with that in many ways. Okay, you could undersample the majority. If I have records in millions and billions, I think I can undersample, right? I can undersample over there. But if the data was slightly lesser, if you were running in few thousands, you would be advised to actually oversample the minority class. The minority class oversampling, when you're doing, it could be duplicate or it could be synthetic points. Like I said, if you have two positive labels and you could sample a point from the interpolated line between the two. Okay. But let's take this particular case study. I am undersampling. Okay. Now, before we go into the metrics, how will your formulation in logistic regression? What do you do? You're predicting this probability of y equal to 1, this conditional probability given the input vector, the feature vector, right? You're doing that, and that is, if I go into that ratio, that's the first ratio on the left hand side is called odds, right? In logistic regression, log of this odds is a linear function, W transpose X, and when you solve this particular equation, given that probability of y equal to -1 given X will be 1 minus probability of y equal to 1, right, given X. So if you solve that, you will come up with your vanilla logistic sigmoid function logistic regression model. Okay. Now, look at mathematically look at the implication of undersampling here. I'm going to undersample my negative class, okay, in this particular case by a fraction r. So if you look at this conditional, if you look at this expression of conditional probabilities, this is how it translates. So second equation, PR prime is actually on the sample. Okay. Now, the prime that is on the sample, I'm making one assumption, and which is not a wrong assumption. The conditional probability of x given y equal to -1. We're making an assumption that doesn't change. And I think that is fair. Given a class, right? I mean, it could be flipped other way around, but given a class, the probability of this x doesn't change. This is fair. But in that sample, the probability of y equal to -1, that changes by the fraction that I have sampled from. Right? So it translates into this equation, and eventually if you see the log odds of the original population is actually translated or shifted by log r, log of r, plus the log odds of the sample data. You trained your model on the sample. Remember, we are talking about undersampling. Right? So I'm training my model on the sample, on the prime part. I've undersampled. But my actual probability has changed now. The estimates would have changed. Okay? So I need to address that. Or in fact, I need to ask the question now that when I'm going to use this model, do I need to address it? If I were to simply rank my content by the response probability, simple rank it, then I don't think I need to shift it by log of r. I don't need to bring in that extra computation because this r is a constant, log of r is a constant. Does that make sense? Any questions? Okay, I'll proceed. Yeah, so in ranking, it wouldn't make sense. It won't make a difference because we are shifting it by log of r. But if I were to rank, so this is the last question, right? Why does this matter? If I were to rank by expected money that I will get, now my true probability has changed because it's no longer, it's the probability from that undersample data that I have got, right? My true probability has changed and I have to shift it back. This is reflected in the graph below. That graph is called calibration plot. What is calibration plot? On y-axis, you have the actual CTR and click-through rate or response rate. And on the x-axis, you have the predicted rate. Okay. The relationship should be linear as you would see on the right graph, the graph on the right hand side. It should be, the correlation should be 1. But if you see it here, the angle is less, right? Less than 45 degrees here. And this is because, and if you look at it, you will see for a given value of a CTR, my P click, the probability of a click, right? That is higher than the actual CTR. How do we plot that? I will explain that. How do you get this plot? But you will see that I'm over predicting now, right? If I'm over predicting, then the money also that the expected revenue that I'm also generating, I'm over predicting that also. Expected revenues in this particular case in click-through rates is the probability of click times the revenue that the click will generate. Right? So even the money will be misrepresented. But had I added a factor of log r over there, this is a plot that I get, and this is a relationship that I get. So I get the right probability. This is called calibration. How do you calibrate? How do you plot this graph? Is a different thing. You do one thing. You have your input records. You have your probability, right? So your training data or test data, you have the probability. You have the records. You have the probability, and you also have the labels in there, the true labels. You sort them in descending order by their probability. Okay. Then you group them. Let's say 1,000 impressions, 1,000 records. Okay. In that 1,000 sample, you figure out what was the actual click-through rate because you have the actual labels, 1010. You figure out the rate there. So it will be sum of all the actual labels divided by 1,000, right? And you also take an average of P click. So you will get 1 point on that graph. And since you have sorted, you have chunked your data into multiple points. If you had hundreds of such million points, 1,000 impressions won't make a difference and you will get this plot. This is a reality check. How are your predictions faring against the actual values that you're getting? So this is one implication. This is how do you use it in production? How do you actually deploy your solution? The other implication is on the metric itself. How will be your metric impacted? Okay. One of the impact, some metrics are immune to this change, distributional change. Some metrics are not. So if you look at ROC, AUC, it will not be impacted by this undersampling. You go and refer this particular page, but the entire reason for that is if you look at the plot of ROC, AUC, it is on the false positive rate and true positive rate. The denominator there is the class distribution for total positives and total negatives. They are not, precision is impacted because of the distribution, but these x-axis and y-axis, they are not impacted because of the imbalance. Go through this paper, this explains it a lot. So PRAUC will be impacted because now my distribution has changed. RIG, relative information gain, that I talked about, that will be impacted, but not ROC-AUC. Will I go for sampling or SMOT? It's an experimental choice, to be honest. So sampling, if the data size is huge, I could go for undersampling. If the data set was small, I would go for oversampling or SMOT. That is true. Yeah. But random sampling on the class. So it's the majority class. More often than not, the majority class is the negative class. So I'll sample on my negatives randomly. But after that, you would need to observe the performance metrics. How is sampling strategy also impacting? So this is one thing that we were talking about, right? How did sampling? Why did sampling matter now? Because if we were to rank by money, then it has a change. Now there's another factor. Remember, we are talking about point-wise classification. I am using so far in that particular example. We talked about this particular the ratios and everything, but it was logistic regression. This is an example of logistic regression. What happens if I use random forests or the boosted decision trees or decision tree for that matter? Forget about GBDTs. But if you want to use a single decision tree, or you want to use SVMs, you want to use neural networks, right? The output in those cases is not probability always, right? And even if it is probability, it is skewed. It's not the real probability. Okay. You will have to do something called calibration. Okay. So this was the this is the calibration plot. But then to get this linear correlation at 45-degree, right, correlation of 1, you need to do a process called calibration, and that you can do in a couple of ways. Isotonic is one. In isotonic, you do make an assumption, and which is a fair assumption, that higher the score, higher the probability, which is fair, right? So you can do that. You can refer to this paper by Charles Halkan, where we are talking about it, where they talk about the calibration. For example, in Platt scaling is used. Have you heard of SVMs? But SVM gives you only distance from the hyperplane. How do you convert it into a probability? Can you raise your hands? How many of you are aware if you want to convert your distance from the hyperplane into probability? So Platt scaling is that. So what you do is, it's effectively what you is a logistic regression, okay? In Platt scaling, you got your output of the SVM classification as a distance from the hyperplane. You use that as a feature, okay? And then you fit a sigmoid with AX plus B as two parameters. A and B are two parameters. X is now the score which has been generated by your SVM. Okay? That process is called Platt scaling. So you convert into that. The whole point is that not always the models that you're developing, how are you going to use it? If you were to rank by expected money, expected revenue, then you needed to get probability, and for you to get the probability from certain models, you have to convert first of all into the right probability. Some models will give you probability, some models will not. Even the ones that give you probability, for example, decision trees, random forests, you can do majority voting or averaging and all those things, they will give you probabilities, but they are not the calibrated ones. So you need to do the calibration. The other thing is how are you going to use it? If, for example, if you're going to use in a multi-objective setup, that I want to maximize my revenue, H money, right? But I also want to ensure that the click-through rate is significant. It's not that in, let's say, in e-commerce, if I have to show you on recommendations, right? I can show you a TV also, and from TV I will get high revenue, right? And I can show you also an apparel, a T-shirt, right? The revenue that I will get from that is not going to be high, although some part of it will be absorbed in the probability of conversion. That the probability of conversion, every time I show you a TV and an apparel or a T-shirt, the probability of conversion of a TV will be lower than probability of conversion for a T-shirt. Yeah. So, they translate into features. So the image of the user that you're talking about, or the fingerprint of the user, right? The signature of the user, that can be thought of as feature vector. For example, if you had even the raw data about the user, I can do PCA on that. PCA is some representation in a latent space, in a different dimensional space of that user, and I could use this as features. So these things are features. Response modeling, for response modeling, you can use them as features. Yes. Through plat scaling. So then in that case, you will have to go back and plot this, and you have to see that if you're getting the probabilities, are they calibrated, rightly calibrated or not? So now, once you've got the probabilities, that is the probability of the class itself, and you can use them as it is. I hope I answered your question, right? The image of the user that you're talking about, it's nothing else but a feature representation of the user. Yes, we can. Yeah. In fact, nowadays, you will, okay, let me ask this question back to you guys. How many of you have heard of this term called embeddings nowadays? So that's what you're talking about, embeddings. And embeddings do play a very significant role nowadays because it's the projection of a user in the latent space. Right? So embeddings is such an example. We were recently doing relevance modeling at Flipkart, given a product and a query pair. For a given query, if this product is relevant or not. If I was using classical feature set, right, of the product and query, it will simply look into what is the textual overlap between the product and the query, right? What terms are overlapping? Now, those terms you can go into subwords also, so that spell mistakes can be addressed. For example, if the shirt, people can, if I use bigrams, character bigrams, I can split it into SH, HI, IR, and RT, these kind of subwords, right? Then if someone mistakenly has typed in chart for short, then only one character and then two bigrams will be impacted, but rest of the bigrams won't be, character bigrams won't be impacted. But my point was something else. I can, the moment I'm just using textual features, right? And maybe I could use some historical features. That query product pair had some history also, I could use that. But if I use that, it gives me a degree of relevance, yes. But what I found was that when I started using the embeddings of the query, of the product as features themselves, right? I projected my query into a small dimensional space through neural networks of 16 dimension or 32 dimension. I projected my products also simultaneously into 16 dimensional or 32 dimensional space. It was more, but I mean, for practical reasons, I'm giving you that. So now if I have user in 16 dimensions, not user, query in 16 dimensions, product in 16 dimensions, I've got 32 more features. And if I now feed it into a random forest or a decision tree will be able to figure out how each dimension of query is related to other dimension of the product. It can do that crossing, right? Does that make sense? Okay, so we can feel free to ask and bug me on these questions afterwards also. So yeah, I mean, answering that, these things definitely help. Here I was talking about multi-objective. So the probabilities that you've got, if relevance is, let's say, 10,000, I mean, it's on a scale of 1 to 10,000, right? And your PCTRs or PCVIs is on a probability between 0 to 1. And I simply sum them up. Then you will know that your PCTRs and PCVIs, the PCVI is conversion per impression, by the way. CTR is click-through rate, the probability of click and probability of conversion. And when we say conversion is a purchase or a buy. Right? So in that case, if the relevance scores are of the order of 1 to 1,000 and probability scores of conversions and clickability is on a scale of 1 to 1, or sorry, 0 to 1, and if you add them, then you will not get too much benefit out of PCTR models or PCVI models, because relevance score is dominating, right? So just be aware of that. Keep it at the back of your mind. These are very smell test kind of a thing, but sometimes these things happen in practice. How do we response model? How do we actually model in practice? Okay. Especially when the data is large. Okay. We always start with the linear models, and that is the truth about industry. You start with linear models. It gives you a baseline, and then we throw a challenge back to the other models, neural models or the nonlinear models. Beat that. Okay. You start with linear models. They're simpler, like I said. They also scale very well. But if you have to bring in non-linearity in those models, how do you do that? You do something called feature crossing. Okay. So in my feature vector, I could have something called user ID as a feature, product ID as a feature. User might have a very high click-through rates. Okay. The product IDs, they could have very high click-through rates. But it's possible that this user and a product combination, this is called cross, user and product, the click-through rate there is very poor. So if I incorporate that as a feature, that is also going to help me when I'm going to show this product to this user. That on its own, the product was very clickable. On its own, the user was also very clicky user. But in the presence of, I mean, when they two come together, actually, it may not be. So we do crossing of the features. These are called conjunction features. Okay. The IDs are, like I said, you could create one hot encoded vector of the features, these ID features. Any feature which is continuous, you can break it down into ranges, discretize them. So let's say if I have a value from 1 to 10, okay, I can break it down into 9 or 10 buckets, 1 to 2, 2 to 3, and so on and so forth, right? And each bucket, if the value lies in any of these buckets, I'll flag it as 1. I'll populate that feature as 1. Otherwise, I'll populate it as 0. So even that can be converted into a categorical variable. Why that is helpful? At runtime, now the weights that you will be learning will be for these categorical variables. At runtime, the value will be either 1 or 0, right? So all you have to do when you have to do the probability computation, first you will do W transpose X on linear models. So the W that you need to get from the model will be only for non-zero features. The zero features will not make any difference. So from operational point of view, it simply becomes a sum operation. You don't have to do any multiplication. You simply sum up those weights. Does that make sense? Yeah. So these are the efficiencies that you are talking about. Okay. The other tricks and techniques that you need to be aware of is, let's say I'm doing personalization. Okay. A user, if for a given user, I have enough information about that user, I'll use that user. Remember, I'm still talking about these categorical variables, discrete variables, one hot, which are represented as one hot vectors, right? Now, if for a user I had enough history, I would learn the weight very well. But what happens if a new user comes along? Can I use some proxy information about that user? The image that he was talking about, maybe that could help, right? The image could be an explicit image or it could be an implicit image. Implicit image is when we talked about embeddings, latent vector. I got that vector, but I could not put a finger on the dimension, any index of that vector, and say that this index corresponds to this particular concept. Right? On the other hand, I can have the other information about the user. It could be the gender of the user, age group of the user, geography of the user, maybe the purchasing power of the user. If I could have those features, then I could, these are called backup features. If I can't use user ID as a feature, then I'll try to use gender. For example, if you are buying kurti, right, and you are a new user to me, I know that the male user most likely is not going to, the probability of male user buying kurti is going to be very less. So that feature is going to become helpful, even though I don't have enough history about that user. Right? So you back off. These are called coarser features. You start from fine-grained features about the user, which is user ID in this particular case, and then you start to back off, create hierarchy of features. Does that make sense? Yeah. Mm-hmm. How does that happen? That's called retargeting. Remember I talked about cookies. Advertisers are notorious for that, and platforms are notorious for that. Google is making a change over there. But what happens there is, there's a cookie on your platform, and that cookie is shared with the other companies, advertisement companies. Then they know that, okay, this is this user. Then they do a cookie matching, something of that sort. Now, so if you shopped on one website, Google will, until you click on it, until you purchase, maybe even after purchase, they won't leave you. When you go to another site based on, because they've figured out your inclination towards that product, they will continue to chase you on the other websites also. But that is, the underlying reason is that while you believe that your user ID was put on one particular website, it was shared on the other one. The only thing is that it's a cookie which is shared, which is a hashed value. So they can't trace back to you that you are the user. But for websites, it doesn't matter. You hopped from one website to another one, and cookies are sufficient for that. They don't need to know that this is Surinder actually here, right? This user is Surinder. They don't need to know about my email address, my address, or anything like that. So no PII information is shared, personally identifiable information. But information, identity nonetheless, and identifier of the user is nonetheless shared. Sorry? Yeah, this is the paper that we were talking about, the feature hash. So now I just talked about this thing, right? When a new user ID comes along, at runtime, let's say you trained your model, okay? You had 100 users in your system, 100 products in your system, or 100 documents in your system. When you're learning, you'll be learning for those 100 users. Okay? There are multiple ways, and I'm still, as of now, focused on using categorical variables. So user ID as a feature. Otherwise, like I said, you will have to fall back on some other representation. Image is generic representation of the user. So when I do this thing, I had I said 100 users, right? So I had 100 dimensional vector. But on the website, a new user comes along, 101 user, right? How would I deal with that? So at training time, you also could do one thing. Of those, out of those 100, you sample first of all those users who have given you enough information. Maybe that translates into 90. But you still train with the 100 users. The rest 10 users, you say that don't know. So you create a don't know index. Okay. So now the 101th user which will come to you, you will map it to that. Now there is a overhead when you are mapping your users to these indices. You will have to maintain this index. Right? Is there a shortcut to that? Right? If I have to do now 100 users mapping, this is fine. But if I have to do it for 100 million users, 200 million users, 300 million users, for Google, it will, Facebook, if it has to be done for billions of users, maintaining that index is going to be expensive. Similarly, for the web pages, products, maintaining that vector is going to be very infrastructure wise, memory wise, it's going to be very expensive, right? If it can't be held in memory, then you will have to distribute it. The moment you distribute it, then there are other challenges, and so forth. So coming back, can I bypass that? And the answer is yes. Professor Anirban answered that along with his fellow researchers. The answer is feature hashing. You create a, I mean, just like in hashing, right? In hash tables, you still create a very big vector, and you take an input as a, you take value as an input, and you map it to one of the cells in that vector. That's all you are doing. And in this paper, they also talk about that it also has some sort of regularization effect. Okay. Now I don't have to maintain this meta information, that what was the index of this user if I use this user ID. As long as I use the same hash function at the runtime, also at prediction time, I will get the same index for that user. Does that make sense? Okay. Sparsity of the features I just talked about, 100 million users, or let's say I have got 500 million users on my platform. Yeah. But a request is coming only from one user at that point in time. So that 500 million dimensional vector, only one entry is present. So you store them in a sparse format. You simply specify the index at which the value is there, and optionally you specify the value. If the value is 1 or 0, then you don't need to specify the value. But if it was other than 1 or 0, then you specify the value also. So this is the sparse way of keeping the data of that vector. You simply keep the vector where the value was non-zero, and optionally you keep the value also. Right? Now, here's the thing. When you have multiple such binary features, user IDs, it is very similar to coin toss. Effectively, I'm learning. So if I tell you what is the probability of a coin 1 landing with the probability with the head, actually if I toss it now, what will you do? You will first, basically you would have done some experiments, and maybe you would have tossed it 100 times or 50 times. You would have gotten an estimate. Had you tossed it 1,000 times, you might have gotten a better estimate in decimal places. But nonetheless, you're tossing it, right? In a 1-0, forget about anything else, but in a linear regression, because log odds and all those things I'm not going to cover. But the weight effectively, if I simply look at this relationship, if the feature is going to be 1 or 0, then weight is that probability effectively, right? That coin toss. If it's a feature in my weight vector, right? Any feature which is appearing n times, and then I have to figure out how many times will I get a response, positive response, 1 or 0, then it's a coin toss. Now, if I have 500 million such coins, right? It is equivalent to saying that I am doing coin tosses of these 500 million coins, different coins. And then I need to figure out how many times will they land on head. That is how many times will they click. Now, what's the you see certain users, I talked about Pareto distributions or skew distributions in the network. So certain users are more frequent on websites, on e-commerce platforms than other users, right? Now, because of that, their frequencies will be different. Some users would have appeared if I have used 1 month of training data. Some users might have appeared only 10 times. And 10 coin tosses for those users are not sufficient for me. Right? But for the others who would have appeared for, let's say, 1,000 times, 10,000 times, right? I would have enough information about them, and I'm confident about it. Okay. So I have to address this in real life. When I'm modeling, I have to address this disparity in the frequency of the feature. So in your classes, you learned about learning rate, right? How many of you are aware of learning rates in the in machine learning models? Okay, fine. Right. So we use learning rate, the loss function that we use, so that the step size that we are using is we can control it through learning rate. The more number of times I see that particular feature, right, or the more number of times I iterate. Like you guys have also gone through Endo-NG's courses, some of you might have, right? We're saying that the learning rate can be decreased over a period of time. If you keep it constant, there is a probability that your model may not converge. The minima that you are seeking, the loss that you are minimizing, it may not converge. So You want to have the right learning rate, the step size. If you take it too big and keep it constant, then you will keep on fluctuating. You will never converge. But if you keep it too small, then the convergence rate will be very, very slow. So you adapt it. Okay. So in the beginning, you take big steps, and as you increase the number of iterations, the step size reduces. So that is called adaptive learning rate. By the number of times you are, by the frequency of the iterations, number of iterations. Now here's the thing: in your classical models that you have all learned, the learning rate is same for all the features at any point in time, right? And here's the big difference. In practice, when you are dealing with such large amount of data, when these coin tosses, like I said, the coin tosses are different, right? The frequencies are different. Your learning rates also have to be different. So this is an insight that was found and observed by folks. For example, AdaGrad is such a paper. Basically, AdaGrad is by Ducci et al., which I haven't mentioned, but the references are in the other paper, Google's paper, right? Google, in its own algorithm, which was FTRL proximal, and I'll come to that, they came up with per feature learning rate. So for each feature, you have a different learning rate. And it could be as simple as that, the number of times that you have seen that feature, right? Inverse of that. AdaGrad is something slightly different. I won't go into the details of that. It's adaptive gradient, as simple as that. The name is an acronym for that. Now, ADAM is another learning rate, per feature learning rate. It's a combination of, how many of you, when you learned your SGD or gradient descent, heard about momentum? Okay. So you can combine the gradient update, right, with the momentum. You bring in another factor, which takes into consideration what was the step size in the last, or what was the change in gradient in the last iteration. So you're aware of that. ADAM is a combination of the two. It combines momentum with the adaptive grade. Then there is lazy ADAM. You don't need to understand them. So this blog, actually on the bottom, it's a very good blog. It talks about different optimization algorithms, gradient optimization algorithms. Lazy ADAM is a sparse implementation of ADAM. So when you have features which are sparse, the example that I gave, I have a 500 million dimensional vector of user, but only one of them is lit up, is set to 1 when I'm making a prediction or when I'm training, right? The other features don't make a difference. In such case, lazy ADAM basically helps. And we have seen this thing. So we were training in Flipkart, we were once training a neural recommender system. Okay. It was a matrix factorization algorithm, but neural matrix factorization. Okay. The epoch time, when I was using ADAM, the epoch time was, per epoch, it was taking around 1 hour, which is pretty big. Okay. Even if I have to train it for, let's say, 10 epochs, it translates into 10 hours. And I hope that in 10 epochs, my model will converge. It wasn't. But 10 hours itself was or 1 hour per epoch itself was a big dampener. And then we switched to lazy ADAM, and our training times, basically per epoch time, switched from hour to 6 minutes. And so these are practical things that, but remember when you have to use it. I mean, it may not work every time. So there has to be certain conditions. Sparsity is what I'm talking about. Sorry? Then you will have to, I mean, lazy ADAM in that case also would be better, as long as there is enough sparsity. The moment the density increases, right, I think the gains will start to diminish. Okay, if you're interested, this will wake you up a bit. How many of you attended the Bayesian logistic regression workshop class? And how many of you understand it and remember it? Cool, good. Remember we talked about the uncertainty in the parameters, right? You were learning W transpose X, right? The W's that you were learning. And we said that one of the requirements for me is to figure out the uncertainty in the estimates, right? can I make that W also come from a normal distribution? And yet again, just to keep things in perspective, it is because of you are learning from samples. So when you're learning from samples, there would always be variance in the estimates. The average height example that I gave you of the college, if you choose different groups, they will have different estimates. And when you plot them by central limit theorem, you will find that it follows normal distribution. Right? In the same vein here, you say that your parameter itself is distributed, and this is where the Bayes rule comes into play, and hence the name Bayesian logistic regression. You have a posterior distribution. How many of you understand Bayes rule? JEE में आया तो कुछ तो थोड़ा बहुत हो गई. But when it comes to distribution, right? When it comes to distribution, it's a basic thing. When it comes to distribution, you have a posterior distribution. Posterior is after observing the data. Okay. Then before that, you have prior distribution. So for weights, what we are saying is that you believe that the weights are a priori they are distributed normally, okay, with a certain mean and certain variance. That's prior belief. Then you saw your data, and then you said, if I had picked a point from this distribution, from prior distribution, what was the likelihood of observing this data? So P of W given W, P of data given W. This is likelihood. When you multiply both of them, you get a distribution of the posterior parameter. How many of you know what is a conjugate prior? Okay, no worries. If I made, so let's take a different example. Leave this thing Bayesian logistic aside. I'll give another example. Let's say I'm doing a coin toss. Okay. And I'll translate coin toss into Kohli also. Virat Kohli, how it's related to him also. Okay. Let's say you're doing a coin toss, and I want to understand what's the probability of this coin landing on head. Let's do an experiment straight away. What do you think will be the probability? I mean, you don't know anything, so you start with some belief, some assumption. You say that, okay, it's a fair coin. I'll say it's 0.5. You start doing this coin toss multiple times, and when you have done only 10 tosses, right? Maybe it's a chance, by chance, that you would have seen, let's say, it landed with 9 heads and 1 tail. Okay. So if I simply looked at the data, the probability of it being landing on head next time would be 0.9. But if I knew fairly confidently, this was a fair coin, this is by chance, this is anomalous, right? Then I will temper that by the previous belief. Now coming to Kohli, Virat Kohli, let's assume that I just have one information about him. Will he click or will he not? Okay, will he perform today or will he not perform today? Right? That's the example that we're saying. You have seen his recent performances, so you will say just on the basis of recent performances, you will say he will not click, right? But Team India has seen his performances over the last 10 years or 12 years. They have a prior belief about him, right? They will say, yes, the likelihood of him not performing has begun to increase, but if I look at my prior belief, and I still believe that belief is right, okay? So now instead of him failing 90 out of 10 times, maybe that the probability will change to 90 out of 100 times. From 90%, maybe the probability will change to 40% if you relied on the belief. Now let's come to, we were talking about conjugate priors, okay? When I did a coin toss, that had a Bernoulli distribution, 1 or 0, right? That's a Bernoulli distribution. If I did translate it into n tosses for the single coin, I will have a discrete, but still a binomial distribution. What is binomial distribution? The probability of seeing 1 success, 2 success, 3 success, 4 successes, and so on and so forth. So I will have a distribution like that, right? Now marry it with, and if I look at the probability, that will be by, leaves aside some constants. What will be the probability? It will be of seeing n successes, it will be, or x successes, p raised to power x, and 1 minus p raised to power n minus x, right? Now you look at the two parameters here, p and 1 minus p. The exponent is x and minus x. Okay. So it has this particular shape. The binomial distribution has this shape, right? Bernoulli, the number of trials is 1, so n becomes 1. Okay. The probability of success being x, you can manipulate that. The belief that I was talking about, right? On that, I can have a beta distribution. How many of you understand beta distribution? Not many. Binomial, how many of you understand? Good, that's fine. Bernoulli also, I'll assume that people will understand. People who understand binomial. Okay. So beta distribution is what we're talking about. Now beta is a continuous distribution on my parameter now, the p value that I was talking about. Okay. So I'm saying it comes from a beta distribution, and the probability is defined by that beta probability distribution. It's not a Gaussian distribution. It's a beta distribution of a different sort. But why I'm telling you that, the functional form of beta distribution is of the same nature. Okay. It will have p raised to power some alpha, 1 minus p raised to power some n minus alpha, okay, or some beta. Okay. It's beta, actually the parameters are alpha and beta. So these are two exponents. Now if you combine it, multiply it, let's go to the Bayesian rule. If I multiply it by my likelihood, the binomial or the Bernoulli, my base is same, my exponents will simply sum up, correct? So the prior was beta, okay, and now if I look at these exponents summing up, okay, my posterior is also going to be beta. If that happens, we have chosen such prior for mathematical convenience, okay, so that these exponents can be summed up. Okay. This is called conjugate prior. The shape of or the form of the prior and posterior is going to be similar. Okay. Now at the bottom is that actually the maybe I don't know if I could zoom. So this is beta Bernoulli. So what we are trying to say is that as you keep on seeing the successes SI, right, your beta distribution over the parameters, you started with some belief, alpha and beta, about the parameters, about that coin in the case of coin toss, right? You started with alpha and beta, but that parameter, as you keep on seeing successes and failures, the probability of coin toss, right, that will also keep on changing. Now there is a good possibility that the coin that we give an example, the actual probability of landing, it was a biased coin. The probability of landing on head was 0.7. It was equally far off from 0.5 and 0.9, right? When I started. So my prior belief was wrong. My frequentist approach, which when I simply looked at the data, that was equally wrong because it suffered from the lack of the sample size. As I keep on getting more and more data, my data will start dominating, but I will not be thrown off because of this the sparsity of the data, right? Now this is the same effect that happens on your parameters also. Okay, when you're learning the parameters and when you're saying that there is an uncertainty, you start with certain beliefs about the parameters, and then you update those beliefs by observing the data. This is Bayesian logistic regression. Okay. This is slightly, I'll leave up to you guys to read this particular paper from the Sheppel et al. But the point is now, the prior that you're applying on your data, right, or on your parameters, you can do a couple of things. The beta prior, or in this case, actually, it's a normal prior. Okay. If you look at it, this relationship, the lambda and QI, they have uncannily used lambda here because lambda is the term that you use in your regularization in your classical ML models. Okay? And when you use Gaussian prior, it is the precision, it's the inverse of the variance. So that there's a relationship. So the regularization that you're doing in your classical way in MLE is a Gaussian prior. If you are using L2, it's a Gaussian prior in your map estimate. So maximum a posteriori estimate, right? And maximum likelihood estimate, they are related by that. What they've done is They've simply said that this lambda, instead of regularizing by lambda, I'll regularize each parameter by lambda I instead. Okay, that's the laymanish explanation of Bayesian logistic regression. If I'm imposing this thing, now this also has a good effect. It's a per feature regularizer. Remember, it's still different than per feature learning rate. There we were talking about learning rate, but this is per feature regularization. This is slightly different. Okay. Once I do that, these are the equations. I mean, with this, so you can manipulate and don't worry about this thing. Eventually, your parameters, right, WIs, you will have a distribution on that. Typically, you simply learn the mean value of those parameters when you do the estimation, but now you will have the mean and variance. Once you have mean and variance, there's a beautiful thing that you can do. Okay. How many of you are aware of explore exploit? Okay. Multi-arm bandits, Rishabh talked about it. How many of you are aware of multi-arm bandits? Okay. They're connected, but the point is this. Let's say you have 10 slot machines. You want to try out each machines, you will spend some money in there and you will get money back. Maybe some machines will give you money, some machines may not. You started with, let's say at this point in time, you have already explored 5 machines. Okay. And you found one machine that is giving you a lot of revenue. I mean, that's giving you a lot of reward. So here's the question for us, right? Do we keep exploiting this particular the machine that we have found, or shall we explore the rest of the 5 machines? If we do the exploration on the rest of the 5 machines, there is a cost. I lose money. So there is an explore and exploit trade-off. I can keep on exploiting, but I also have a hope that there might be another machine which has a bigger reward, right? And I'll figure out the right rewards. So I need to figure that out. How do I explore? The simple strategy is this. There are a couple of principles, but if you've already explored an arm enough number of times, then you already have the confidence in it. So the uncertainty in that should be lesser for you, right? That will it give me enough reward or not, right? Because that machine would have given you some different rewards. Not every time it would give you the same reward. Let's assume there is a distribution of rewards. Okay? But if you have explored that machine enough number of times, then you have confidence about the reward from that machine, but other machines you don't have. So you can explore. And as you keep on exploring, and this is the same Bayesian theorem, right? Bayesian. You started with an assumption, with the belief that they will be rewarding, but as you keep on getting more and more data, your mean estimate of the reward, mean reward estimate from those machines will keep on developing. They will stabilize somewhere. So you can explore in multiple ways. One of these ways is this. Mu times, which is the mean estimate, what has been the mean reward that you have got from that machine, right? Alpha is a parameter, and the uncertainty in that machine. So in the beginning, your uncertainty will be very high. Mean could be something else. So in the beginning, maybe you can explore more. Okay? Alpha controls that value of exploration in explore exploit. Okay. This principle is called, if I keep alpha as 1 or increase alpha, in Bandit's world, it's called optimism in the face of uncertainty. When I'm uncertain, I'm optimistic that the unexplored items will give me rewards. So I'm optimistic and I'll explore more. It can burn both ways. But then there are approaches when you basically, every time you burn your hand, right, you feel a regret. Why the hell did I try this arm, right? And multi-arms. So the goal is that over a period of time, your expected regret will reduce and it will converge towards the best policy that you should have actually taken had you known a lot of information about these machines. So let's say you've explored today and tomorrow also, you know that this is the distribution which is going to remain same. But by now you already know, you have converged on that, right? So in expectation, over a long horizon of time, your reward will stabilize, and there are multiple proofs and all those things. Don't need to go in there. But my whole point was, in practice, when you are developing models, when you are developing, and when you need to have uncertainty. When I showed red Nike shoe, right? One of the problems in machine learning areas is that of feedback loop. I showed you a result. You gave me a feedback. Users gave me a feedback. The products which were clicked more, I will now keep on showing them more. And the products which have been uploaded by the sellers, right? New products. It's called cold start problem. They will never see the light of the day, right? So my system, the overall health of my system, right? The economic health of my system can deteriorate very fast, right? So the whole point there is that while I'm exploiting, I need to continuously explore the new candidates and build history about them, build knowledge about them. And that is why these models are also critical in practice, that you will have to explore. And the exploration is one of these methods is Bayesian logistic regression. Okay, you got your uncertainty, so variance from the Bayesian logistic regression model, right? You got the mean estimate, and you can explore it like this way. Or there is another way that is called Thompson sampling. You got the distribution of the parameters. Okay, Thompson sampling is an assumption which it simply says that I could compute my expected value over the distribution, right? How many of you know expected value computation? It simply says that if you have the probability, expected values, okay, let me roll a dice, okay, and ask you a question. What is the value that you will see now? Okay, if it's a fair dice, then I can simply multiply 1/6 the probability Pi and Vi. Right? That's the weighted average. Right? That's the expected value. So Thompson sampling says that you have the distribution. So if I sample a lot of points from that distribution and take expectation, sampling a lot of points with continuous distribution is equivalent to integrating it with the value for each parameter. But if it's a discrete distribution, I simply sum them up. But the point is, let's sample multiple points and sum them up. My integration is approximated by that sum, right? Sum them up and then see which particular product, arm, add, all these things are interchangeable in practical setting. Which one of them has highest expected reward? Okay? And I rank my content by that. So now you see, I'm not ranking by my mean weight. I'm not ranking by W transpose X. Okay, I'm doing this expectation, but if you have so many parameters, computing this is going to be very, very complex, right? So Thompson sampling says for each parameter, you sample randomly a point from the distribution. Here in this Bayesian logistic regression, we assumed that the parameters had a Gaussian distribution. So I'll sample a point from that Gaussian distribution because I know the mean and variance of that. I'll sample that and I will use the W star. So now my estimate would be W star transpose X, where this W star is a vector. So I will be sampling from each individual. I'm making an assumption that there is a diagonal matrix. So each feature, the weight of that feature, I'm going to sample the value of that weight from that distribution independently. So now I'm doing, in terms of summation, Wi star Xi, and Wi has been sampled from that. This is baking in the uncertainty here. Or your Wi could be the naive UCB, upper confidence bound. Like I said, you already had Wi's learned. You simply multiply by alpha and uncertainty, you have sigma I. You could do that also. But the problem is that if alpha is positive and uncertainty is positive, standard deviation, then you will always be exploring on one side, on the upper confidence bound. This is why it's called upper confidence bound. And hence this principle is also called optimism in the face of uncertainty, that you're always exploring on the upper side. Does this make sense? So second algorithm is the Thompson sampling, which I was saying expected reward, right? And the expectation you could compute depending upon the distribution. If it's a continuous distribution, you do an integration, otherwise you sum them up. And the one below is a Bernoulli distribution, which assumed that the parameters had a beta distribution on top of it. And the reward was Bernoulli, so 1 or 0. And accordingly, you could update it. And then you can sample from it. It's also called context free, because if you look at parameters are not context free, parameters are contextual. But if I was simply taking the case of coin toss, then I did not take the other conditions into factor. What was the humidity? What was the height, right? What was the weight of the coin and all those things. They can also help me figure it out, that what will the probability of a coin landing with a head or a tail, right? So that is context. But if I simply observe the outcome, and then bake in my uncertainty, that is context free. Right? I'm not using any meta information about the coin. Does that make sense? And we do that in practice, these things. So these are practical algorithms. Okay, this is a nice trick. Let's say I have these, when I'm training my model, right? I talked about hundreds of millions of features, large scale. And for that matter, you even think about millions of features, that is sufficient. I mean, when you've done pruning, feature selection, right? You have millions of features. If I'm not using regularization, let's say I'm simply doing square loss. This is applicable to anything, but even for log loss, it will be helpful. Okay. What will be my weight update? So irrespective of any loss, I mean, or focusing on square or cross entropy loss, if it's a sparse vector, right, you will find that when I'm computing Wi update equation for Wi, individual component, only those weights need to be updated for a given training sample for which the values are non-zero. So even if I had 1 million or 10 million features in that, remember only one user ID was there and one product ID was there, let's say, only these two features need to be updated. The weight of these, if I'm not using regularization. You know, the derivative of sigmoid is, what is that? Sigma times 1 minus sigma. You would have learned that, but that's just right. And when you take a derivative with respect to W and because of W transpose X, so it will be sigma times 1 minus sigma times Xi because of the W transpose X. Okay. So this Xi value, if it, remember we were talking about discrete variables, categorical variables, which would be 1 or 0. So the gradient is now sigma into 1 minus sigma times Xi. Sigma is a constant because I know about it. I mean, I can compute it for a given weight vector at that point in time, at time t. But only those weights will be updated where Xi is non-zero, even in this 10 million, 100 million dimensional vector, correct? Which is fine, which is what I want. I mean, I have just, if I'm using only two features, user and product, that's all I want. And if I had used a cross feature, user cross product, then I would have to simply update 3 features, 3 weights in one iteration of my model, you know, of my stochastic gradient descent, which is lovely. Updating 3 is what we want. And we are memorizing at the same time because I'm learning from the history, which is good. The problem comes when I start using lambda W square, the L2 norm. Right? Now, because of this lambda W square, for non-zero features, it will still be there. I use basically half lambda W square, right? So it will, the gradient would be, the gradient contribution from this component would be lambda times Wi, correct? Now this lambda Wi, if you see, this is independent of my feature. Does that make sense? Maybe I could, I'll just try to write it down if you guys are okay. Very quickly. So this was my sigma. I know that people are online. So, and when I had my loss, the log loss, I'm not writing that. You will find that the derivative of loss, right, with respect to Wi is this sigma 1 minus sigma times Xi, this component. This is the log loss derivation. But if I use regularization lambda times this one, this will also bring in lambda Wi, right? Because of this Xi, my Wi update, Wi new and wi old minus this del of right, because of this one, if it was log loss only, then excise will kick in and I will only be updating for sparse only those values where it is non-zero. But because of this guy, all the wi's need to be updated now. Although they need to be updated by a constant factor for zeroed excise, for this set, wi new would be simply wi old minus lambda wi old. So you can take this out and this will become this. Right? The point here is this, that you need to update all the features. That's the main point that we're trying to make here. All the weight vectors have to be updated. All the weights in the vector have to be updated. Now the cardinality hits you. If you have many millions of features, right, and if you have to update them in one iteration, you're going to run into challenges. This is going to take time. This will slow down your learning algorithm. The convergence will be very slow. Okay. So there's a neat trick. You break your W into these two factors. W is a weight, by the way. So weight vector. What I did there was for a simple component of the weight vector, one dimension of the weight vector. But you could you can take it for granted that this will also work out if it's a weight vector. Now I'll transform my weight vector into these two components. W2t is equal to a scalar times another vector, capital WT. Okay, this is all I have to do. And then I update my st plus 1, the scalar, at runtime by this factor, and it's derivable. I mean, you can derive it. And capital WT plus 1 by this particular value. Now you see the capital W1, WT plus the capital W is what you are updating, and because of that X, it will be X component at time t, which is fine, training instance. X, only non-zero excise will be there. It will be updated only for those values. For others, it won't be updated, which is what we wanted, because scalar has to be updated only once for all the features. So this is a very neat trick. It's been called out by Leon Butu in his work STD tricks, and this was first actually formulated and proposed by Shalif Swartz in their paper. But this is a lovely trick. So when you work with such data and when you're writing your custom algorithms, you will not find this trick actually in some of the libraries. Some of those libraries might be slow to update. I believe sklearn has that too, because we've seen it even when we use regularization and all those things, it's pretty fast. So you were asking, right? Can I use both kind of features, dense features and sparse features? The answer is yes. That's typically how you work in industry. So if Facebook paper, for example, in Facebook, they had a paper, practical lessons for ad click prediction at Facebook. They take both the features. You will take the historical clicks and impressions of the ads or the results, as well as the categorical representation of the features. So you do both of them. The challenge with the count features is this. If the coin toss example, right? If I toss the coin 10 times and I got 9 successes versus 1,000 times or 100 times, and I got 50 successes, right, out of 100, or 200 successes out of 1,000, right? Which one of them is more reliable? More the better. It's no-brainer, right? So this is something, when you are using counts, this is something you have to be aware of. Okay? That there are sparse counts in your model, in your data, and you're using them as features. So they can throw your model off the guard. Okay, they can corrupt your model. So for such things, you start smoothing. How many of you know naive Bayes for text classification? So there we use also in some formulations we use counts. of the terms. For spam detection, it's used. But the point is the counts, wherever we use counts, we use Laplace smoothing over there. We add some pseudo counts, right? Otherwise, the probabilities will multiply and you will, unseen guys will have zero probability. So now naive base will have that problem. Similarly, when you're using counts to deal with this problem. So if I told you, remember we talked about beta prior and we said that the coin is fair, right? But by chance, I observed that it had 9 successes out of 10 trials, right? But if I said no, only when I toss a coin 100 times, I get enough confidence. Only then I will get, I'll trust the numbers. Okay? So you do one thing and you have a belief that this is a fair coin. You have an unbiased belief. Okay? So you do one thing, you grant some pseudo trials and pseudo successes. So any estimate of the probability of head, you simply say number of times the head was observed plus some factor C, okay, or S, which is success, okay, divided by number of trials plus another factor, which are, these are the pseudo trials that we are talking about. Okay. Now you see, if I gave 50 heads to begin with and 100 trials, now you add 9 trials, 9 successes out of 10. So that your estimate now would be 59 out of 110, right? So it is shrinking towards the mean that you started with, the belief. This is called shrinkage. Okay. The good thing about this is that your bias will come down. I mean, sorry, your variance will come down, bias will increase, right? But your variance will come down for these small counts, sparse counts. And that is something that you would want, that you want to reduce the variance, because higher variance in the features and everything, it's going to throw off your models. Okay. So this is something that you do. In case of clicks, response modeling, the case study that we are still dealing with, right? If I'm using these counts as features, clicks and impressions, I give some pseudo clicks and pseudo impressions to those features. Okay. And how do you come up with these C's and I's? Is slightly more involved. You can read it about empirical base. You can learn these parameters of this beta distribution. This is akin to beta distribution, like I told you. The coin toss example that I told you, right? And I got this estimate. This is MLE estimate only, maximum likelihood estimate. But now because of the prior, it became a map estimate. You can read about it in empirical base, and there is a very good explanation on this blog. This guy talks about how they have used in baseball statistics. There's a company called Sabermetric actually, which used it a lot and quite successfully. We already touched base on this. So best practices, that if you want to explore and exploit, you need to model for uncertainty. One of the ways was, we discussed, one of the ways was posterior distribution. I learn a distribution. Distribution will have a mean and a variance, and then I could use that mean and variance as a measure of uncertainty. FTRL does it in a different way. We'll come to FTRL. The bootstrapping was another thing. Yeah. Okay. When you are dealing with large data, you have to train your model. So far, I've talked about how you will train a model. But that translates primarily learning on a single machine. I haven't talked about how will you learn such data. I mean, sometimes you won't be able to fit it on the single machine. Random forest, right, is easily parallelizable, right? The trees, they don't have any relation with each other. So they can be learned each other, and then you have an ensemble of the two. So there are papers around it. There's a paper named Planet. That's an acronym. But it talks about how do you parallelize random forest learning, because there are different trees. It's an ensemble. The classical way of there have been other way of ensembling also. Sometimes you will find. How many of you are aware of Netflix problem, by the way, Netflix challenge? You know, it was $1 million competition. And you know the winning solution. It was, I think, it was an ensemble of around 200 models. Sorry, Belcore, yes, yeah. Yoren Bell, I think Yoren from yeah. Yehuda Koren, yeah, from Bell Labs. Right. So they created an ensemble of the models, okay, 200 models, and they found that there were 2 or 3 models, RBMs and Funk SVD models, matrix factorization models. The target was to basically improve the RMSE by absolute 10 percentage points. Okay. And individual models, they were hovering at around 9 point something, and I think that state went on for 1 year or so. Lastly, those guys came together. They created this ensemble of 200 models, and they beat the they beat the benchmark. They won the prize, and those guys actually divided the prize among themselves. Like Professor was saying, Belcour, there were 2 teams actually which combined and joined forces. But the point there was this: ensemble models have great power. You would find these models getting used a lot, but then they come with a challenge, right? You will have to train so many models also. Here, this is one implementation from Twitter. How did Twitter deal with large data for their click prediction model? It's a MapReduce. How many of you are aware of MapReduce? Okay. Anyways, it's a, how do I say it? Merge sort. How many of you are aware of merge sort? Okay, cool. So the idea is parallelize, right? You can divide and conquer. So in the same vein, can I divide my data into smaller chunks? Okay. If I had 100 million data points, training points, I can divide them into 1 million points of 1 million and 100 batches of 1 million points. And then I would want to train my model on those. 1 million points, maybe they can, hypothetically, they can sit on memory compared to, let's say, 100 million. I'm just hypothetically telling that memory, let's say if it's very, you have very constrained memory. Right? So what you do is, you remember one of the problems that we were talking about was throwing the data, undersampling. Even when you have these memory constraints to train on the box, even there you can throw the data. You can do undersampling. You can do undersampling of both positives and negatives, but you can get the data which fits on the single box. Or you could create these 10 batches, and each batch could fit on one machine. Yeah. You train these models in a MapReduce manner. So, excuse me. These batches, the 10 batches that we are talking about, okay, you train them parallelly. So you start with MapReduce, you had 100 million points, you run a mapper. The mapper will divide it into 10 batches. And on that mapper, now you train a model. Okay. So from one mapper, you have divided and conquered. So you're dividing and conquering here. You've got one model per batch, which is per box. Now you've got 100 such batches. How do you combine them? Let's go back to getting the probability estimates from random forest. You had 100 trees. How would you combine them? How would you get the probability estimates? You can either do a majority voting. What majority of the trees are saying, right? That could be your estimate, right? Or you could simply take an average of them. Right? So this is aggregating. The sampling of the data was bootstrapping. So this is bootstrapping and aggregating in combined form. The acronym is called bagging. So when you hear about the term bagging in machine learning, it means bootstrapping and aggregating. This is the ensemble. This is what Twitter has done. Okay. So when you have terabytes of data generated and you want to use that and you don't want to throw it away, you make use of such a cluster setup. Spark is that actually. Spark also does that for you. If you want to use Spark, but my experience, okay, with Spark, first of all, it's MLlib, the MLlib library, that the machine learning component on Spark is very, very rudimentary when you compare it with PyTorch, TensorFlow, or sklearn, right? Those guys are not distributed. This guy is distributed. There is some on the chat. Just a moment. There is a question. Okay, it's all about it. Where was I? Spark. Yeah, so MLlib is very, very rudimentary there. Okay, and So I once trained that ad prediction model that I was talking about, click prediction model. I once trained that GBDT model on my single box with sampling, okay, under sampling, and I could get a certain performance. The same model that I trained on Spark using MLlib, the performance, there were absolute 10 percentage point delta between the ROCs. And then I got in touch with the author of the GBDT on sklearn. He was also a committer on PySpark. And he said that it could be because of the distributed nature, there could be a difference in how they're partitioning the data. Because on trees, you will have to partition the data into nodes, right? At every decision, at every point when you're making a decision, when you're creating the tree. And that could be one of the reasons. And when you are doing it in a distributed fashion, there could be implications, the way it has been implemented for efficiency reasons. But this is my experience, okay? I'm not, don't hold me to it. MLlib for sure is very, very rudimentary, but for simpler models, right? Maybe it could work. However, one thing that I found, here you see, this is classical MapReduce. They use a script called pig script. I think Professor Anirban, when he was talking about his experience in Yahoo, you were using pig scripts, right? Nowadays, you could use Hive and other things, right? Pig and Hive, they are relatable. Okay, but the point is, the learning curve for pig, Hive, and all those things is relatively small. Spark, on the other hand, deals with the large data in memory. It keeps in memory. Traditional MapReduce, it will spill out the data on the disk and then use it. So it's relatively slower. Spark is faster, okay? And it also has these lazy patterns. Unless you have an action, the transform actions. So there is a transform component, there is an action component. Unless you do an action, all the transformations that you're doing on the data, they won't be operated. So you've and then all these things are happening. So there are some optimizations, but the point is the learning curve with Spark, in my experience, for machine learning, has been slightly steeper. Okay, it's not out of the box. But Spark, people use Spark also. And if you were to use single machine setup, in certain libraries also give you that capabilities. sklearn gives you partial fit. You fit on one data set at a time. You chunk it out of memory, you load another data set, okay, and then keep on fitting, keep on within one epoch. If you had 10 data sets, if you split your data into 10 data sets, you can load one at a time, update the model, and then resume with your epochs. So that is, it's slower because you have to do it in the single box, but at least memory management is better. You can still hold it in memory. Instead of holding those 100 batches that I was talking about in memory, which you can't do. If I hold one in memory, that's fine. But I have to do it at 100 times. I can't parallelize it. But still you can do. And frameworks like Keras and TensorFlow, they have something called generator. So you can generate the data, read from the disk and feed it to your model. So that also can be used. But the whole point is, this is how you can do. Now, there are more complicated ways. Downpour is one such system. Remember, I talked about parallelize and then you can aggregate, right? Ensemble, that's one way. But if I want to use the entire data at the same time in one epoch, then I can parallelly update the weights and then send those parameters to a parameter server by taking all the values. So I don't have to update my parameters at the end of the iterations when all the individual boxes have basically run out, okay, or are done. I can do it in each epoch, but that needs a lot of communication. So you need to have a parameter server which will gather all the parameters, accumulate their updates, broadcast it back to the individual nodes. But you can do that. Okay, time check. How many of you want to continue now, or we start tomorrow? I'm venturing into another field of online learning. Okay. We can take a logical break here and we can resume tomorrow. Online learning, so far we talked about dealing with large amounts of data, large swathes of data. How do you do that? online learning actually alleviates all those problems. You see a sample, it follows the principle of you look only once. You see a record. So let's say you are doing SGD. How many of you are aware of SGD? SGD you are aware, right? Okay. Let's say in SGD you do, SGD stands for stochastic gradient update. Let's remove stochastic part out of it. I got, in a day I got the samples and I'm doing my gradient update. Let's say I go through the samples temporally as and when they arrived. I sort them by their arrival times, okay, and I first update on the instance that I saw first in the day, and the last instance that I would have seen in the day. I would update. I would see it in the last and update my parameters in the end. Okay. If I do it this and only once, this is called online gradient descent. In stochastic gradient descent, first of all, you shuffle. You do some stochastic. I mean, you bring in some stochasticity. Right. Number one. Second, you go back and run another iteration until convergence is the criteria over there. There is no until convergence criteria here. You're learning as you go, and we'll take it tomorrow. Yeah. Thank you. I know you guys might be drowsy, but if you have any questions, I can answer. Or once I take a seat, you can talk in person also if you can. Yeah. Cool. Thank you very much. Any questions online? If folks have any questions who are on the Zoom call. Okay, I take it as a no. Cool. Active learning in which setting? See, in this case, I'm not getting the feedback, the labels. Active learning is getting your labels on the right data from the human labelers, right? Primarily, I mean, I'm taking that example. In this case, my feedback is coming from the users. So I am not doing that. I am not correcting my, I'm not getting the right label for the noisy prediction that I might have made in this particular example. So far, I've been talking about response prediction all this while, the running case study that I had. But in certain cases, you can. For example, if I was doing query to product relevance or query to document relevance, because I rely on the human label data also. So what I can do there is, I showed the result to the user. User did not give me feedback. I know that these are not good feedback. Then I make my model predictions on that. If I am predicting very low scores, then I'm fine that my model is fine. But the results which I showed and where I was decently confident, right? And users did not click, or I was in the region of uncertainty. There's also called uncertainty sampling over there, right? So I could take this sample from those records where I was uncertain, and I will hand it over to the human labelers, which we are calling human in the loop, and then I can do active learning. So we do that. That is for those labeling tasks primarily. Can we get good labels, especially where my model is not sure? Sorry. Yeah. So that's a different problem. That's a relevance problem, and I'm not relying on the uncertainty in relevance, because someone has given me a human label, has told me definitely that this is relevant or not. Okay. So in my opinion, I don't think that uncertainty would be applicable over there, although you could do that. But that is primarily applicable when you have noisy data, when you have noisy labels or user labels. Sometimes they may not be reliable. Here the uncertainty could be captured if relevance, if your model is generic enough. You could do bootstrapping, and then you can generate the distribution around the relevance. You can do that, but that will be used for surfacing the candidates, for exploring the candidates. That you could do.